Hello everybody, Dukeless here once again, and welcome to the next episode in the C programming series. So in this one we won't actually do any programming, we have to do a little pre-course so we can properly reason about the things we will do in the next episode, which is the type system. So in this episode we will be looking at bits, bytes, and how to do conversions from the normal number system, the decimal system, which is base 10, to binary, which is base 2. And we will have a look at how to do positive and negative numbers, floating point numbers, and we will get a little bit familiar with ASCII and hexadecimal. So to get started, we will be talking about what is a bit. And a bit is very simply a 1 or a 0. Can't be anything else, it's a 1 or a 0. So, having done that, we can talk about the byte. So a byte is specifically 8 bits, and as you can see up here we have 8 ones. That's an example of a byte, so that's 8 bits. Here's another one where we just 1010 0000. So a byte is 8 bits. So 8 ones or zeros, some combination of those. Down here we can see what those ones mean, or zeros. So if we read it from right to left, we can see that the first 1 or 0 is 2 to the power of 0. So if there's a 1 here, it's 1 in our conventional decimal system. If there was a 0 here, this would be 0. And so on it goes. So 2 to the first is 2, 2 to the second is 4, and so on and so forth. This means that with 8 bits, or 1 byte, we can represent 256 numbers. So from 0 to 255. So 255 is the largest number, and it's the sum of these numbers. So I have already written out some examples here. You can see that 5 in the decimal system, you can see the subscript here is 10, that's the decimal system, is equal to, reading right to left, 101. So the first one is a 1, and the third position one is a 4, as we can see from the table up here. 1, 2, 3, 2 to the power of 2 is 4. So that means we have 1 plus 4. Here's another example. We have 16 in the decimal system, and we can actually see from the table that 16 can be represented with a single bit in the 5th position. 2 to the power of 4 is 16, so that's pretty simple. Now I actually want you to pause the video and try to do the number 42 yourself, and you can unpause it when you've given it a solid try, and we can compare your solutions. Yeah, so pause the video. Now that you've unpaused the video, you can see the solution, which is 001011010. So if I've done this correctly, this should be a 2 plus 8 is 10 plus 32 is 42. Very simple. So that's the introduction to the bits and bytes part. You can try to do more numbers if you want, but I will be moving on now. So now we cover the first 3 points. Let's go back to the drawing program and let's do number 4, converting from binary to decimal. I mean, this should be just as easy. If you do one, you can do the other. Let's just write out a bit string. So let's just do 00111010. That's 4 plus 3, so let's add another 0. Let's just do this. So this is base 2, and what is that is base 10? Well, it's 0 1s, 0 2s, 1 4s, so that's 4, plus 0 8s, plus 1 16, plus 1 32, and that's our entire number. So what is this? This is 30, 40, 48, 52. Let's just do a quick calculator to make sure that's correct. and that is indeed 52. And there's my mouse. And that is of course in the base 10. So that covers that. Now we can take a look at the 2's complement system. So the 2's complement system is a system used in order to represent positive and negative values. So the sign bit is stored in the leftmost bit, where 0 is positive and 1 is negative. We can see here, so this first part here, we can see the first bit, the leftmost, is 0, which means this is a positive number. And we can see that the rest of the bits is literally just zeros followed by a 1 in the rightmost place. So this is equal to 1 in the decimal system. So in order to change the sign, if we wanted -1, we flip all the bits and add 1. So if we want to go from +1 to -1, start with 1, which you can see here, and then we flip them in this step. We get all the zeros are now 1s, and the 1 is now 0. Then we add 1 in this step. I didn't bother to fill in the zeros. And when you add binary numbers, you just do it like normally, you carry. So here we have a 0, we add a 1, so that's a 1. If we had 1, 1, we'd have to push all the bits 1 over because we carry it. But in this case, we just get 1. So the final result is 8 1s, which is equal to -1 in decimal. Now I have another example down here, which is 16 plus 64. This is just some more addition. So this is 80. So we flip all the bits. And here you see when we add 1, we actually do have to carry. So 1 plus 1 is 1. We write down 0. Then we have 1 plus 1 is 1. So we carry and we add a 0. And so on and so forth. Till we get to this step where we have 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 0. So you can now see this is the leftmost bit is 1. So that means it's negative. So this should be -80. And let's actually check a calculator on the internet in order to check that that is correct. Lo and behold, 1011 followed by 4 zeros is indeed -80 in decimal. So that's a quick introduction to 2's complement. I will post some links in the description to the Wikipedia and this calculator so you can read more about it. Now let's take a look at floating point representation. So this is decimal numbers, so like 3.14 or 0.001. So this is a standard we'll be looking at that's called IEEE 754. So in the same way with the 2's complement, we have a sign bit, the leftmost bit, which again 0 is positive, 1 is negative. This is followed by the exponent bits, which is 8 bits. So this is a bit special because you have a bias in the case of 32-bit floating point numbers. The bias is -127. So whatever value this represents in absolute terms, you subtract 127. And that's your real exponent. So you can see down here we have the sign bit, which is positive, and we had 127, which is this, which is now 2 to the power of 0, which is 1. And that's the mantissa, which is 23 bits, and we'll take a closer look at that in a moment. But there is always an invisible 1. This is always present. Which means in this example we have 2 to the power of 0, which is 1, times 1 plus 1 times 0 plus 1 times 0, so on and so forth. Which means we end up with 1.0. Now, the way the mantissa works is that every bit counting left to right is equal to, if we do some cleaning up here. So if I flip the first bit to a 1, that means we also multiply by a half. Or more accurately, we multiply by 1 over 2 to the power of n. That is supposed to be an n, looks more like a w. Completely forgot to say pardon my handwriting. This is an n. Let's do a small n. There, n, small n. So the first bit is actually 2 to the power of 1. So 1 over 2 to the power of 1, which is 2. So this is a half. The next bit would be 1/4, because it's 1 over 2 to the power of 2, and so on. So if we do this example again, if we do positive 2 to the power of 0, because we didn't change the exponent, then we can multiply that by the always present 1. This is always there. And then we change the first bit, so we also tack on a half. And then plus 0 and so forth, you know. So this would then be equal to 1 times 1, which is 1, plus 1 times a half, which is a half. So this gives us 1.5. So that's just a quick introduction to how this standard works. I will again be linking resources to Wikipedia and calculators for this. I've actually opened the calculator now, and I was thinking of showing you the example here as well, just to make sure, 1, that I didn't mess up, and 2, that you can see how the calculator works. So we had this set, I believe. You can see now the value is 1. Let's just quickly compare with my drawing program. You can see 0, 0, followed by all 1s. And originally this was all 0s. This is indeed the same as I wrote. We can see that the decimal value is 1. So if we switch this, we should get 1.5. And so we do. So that's just to show that this works. The system isn't something I made up, this is how it works. And so I just got rudely interrupted by my girlfriend, but that's fine. So I closed the other calculator, I've opened this, and I wanted to show one of the downsides with the floating point system. You can only represent so many values, because there's an infinite values between every integer, right? Because you could just tack on another number, like after the dot, and you can't represent them all. So you can see here, I believe this is the closest approximation of the number pi in 32-bit IEEE 754 representation. You can see we get 3.141592. I believe this is the closest, so we close on, the last 2 is 92. If we just Google number of pi, you can see 3.141592, yeah. So this is the closest we can approximate pi with 32 bits in this system. So I just thought that was important to note, that you don't have infinite precision. So now that you know that, let's move on to the next part. So with that done, we can take a look at the next chapter, the ASCII table, or rather ASCII the system, but we have the ASCII table up. Just paste the standard there. So ASCII stands for American Standard Code for Information Interchange. So what this is a way to represent text. So the computer has no idea what text is, it only knows bits and bytes, or multiple bytes as well, but it boils down to bits. So the way we represent text is by giving number values, because we know we can easily convert between binary and decimal, so we can use number values to represent characters. So you can see here we have decimal value, hexadecimal, and octal. We will only really care about decimal, but I will quickly cover hexadecimal as well. So we can see that the capital letter A has the numerical value of 65. And you can also see they were nice when they figured out the standard. So the next character is B at 66, and so on and so forth. Then we have a space here with some other stuff, and then we have the lower capital. no non-capital letters. So 97 is lowercase a, lowercase, there we go, lowercase a 97, and then it goes all the way down to 122 for Z. And there's also some other special characters there, which we won't be covering very much, with the exception of stuff like null. Because, yeah, we'll cover that in the next episode. But that is just a quick introduction to ASCII. You can look up this table if you want. So, for the final part of this video, thank you for sticking with me so long, we actually will be checking out the hex system, or base 16. So as you can see here, if I can find my cursor, there we are. From here to here, we have the range of hex. So you can obviously understand that we can represent 16 values with this. We start with a 0, we go all the way up to 9, like in the decimal system, but then we add on A, B, C, D, E, F. So that's 10 through 15, the values 10 through 15. So you can see that this can be represented in 4 bits in the binary system, because we can represent 16 values with 4 bits, 15 plus 0. And yeah, so in from binary to hex or vice versa, you can see that the value 15 is F. You can see that from this table. And this confused me a little bit, but this is the notation for hex. You could also do 0x and some bits, or actually that's wrong. You could also do 0x and the value. This is another way to represent hexadecimal. 0x is the same as 16, as in the base 16. So you can see that F is equal to 15. We can see that this is 15. 15 equals F. Very simple. So that means if we have a longer bit string, I'll actually use the 0x notation. If you have F3, for example, this would be 8 bits, because every character, so there's one character and there's another character, every character is 4 bits. And we actually have an example down here, 9E in 16. So the way we do this is we just write the first character, so this should be 9, so that's 8 plus 1, which is 9. The second is E, you can see that E is 1 less than F, so that's 14. That's 8 plus 4, which is 12, plus 2, which is 14. So the total value here is 158 in decimal system. Provided I did it correctly, you can use the calculators to check that I actually did it. And that was basically it for this episode. In the next episode I'm planning to show you the type system. We can cover more of the types and we can create our own types. And now we can actually reason about the sizes of these types, because that's kind of important. But now I have to pick up my girlfriend from work, so I will be seeing you the next time. Thank you for sticking around and I hope you enjoyed it. Bye bye.